Hey, my friend, if today was long or heavy, you're in the right place. This video is a calm, step-by-step journey through how physics quietly built reality itself, from the deepest rules of the universe to the stars above you. Just listen, relax, and let the science carry you gently towards sleep. Chapter 1. The rules before anything existed. When people picture the beginning of reality, they often imagine a burst of heat, a flash of light, or the sudden appearance of matter. Physics invites a quieter starting point. Before we talk about particles, stars, or even space itself, we can talk about regularity. The universe, as far as we can test it, behaves in reliable ways, not because it is polite, but because its behavior can be summarized by patterns that hold across many situations. A law of physics is not a command that the universe obeys. It is a compact description of a pattern that seems to persist. Scientists search for such patterns because the world is too detailed to memorize moment by moment. We build models that capture what stays the same while other details vary. That distinction matters because it keeps the topic grounded. The rules of physics are not necessarily separate objects floating somewhere outside the universe. They may be features of the universe itself, discovered and expressed through our best theories, and always open to refinement as our measurements improve. Even with that caution, the power of laws is unmistakable. A relatively small set of principles can predict the motion of planets, the behavior of atoms, the bending of light, and the currents in a wire. The same core ideas apply in a laboratory and in a distant galaxy. This is a calming fact to begin with. Reality is not a collection of unrelated surprises. It has a coherent structure, and coherence is a kind of quiet. So what could it mean to speak of rules before anything existed? We should not imagine a time before time. Instead, think in terms of logical priority. In physics, some ideas come first, not because they happened earlier, but because you need them to make sense of anything else. Symmetry, conservation, and consistency are like that. They are not decorations on top of the universe. They are part of the scaffolding that makes the universe describable at all. One of the deepest clues we have is that the laws of physics appear to look the same when you shift your point of view. If you perform an experiment today and repeat it tomorrow under the same conditions, you expect the same outcome. If you move the experiment from one side of the room to the other, you expect the underlying rules not to care. If you rotate the apparatus, you do not expect nature to rewrite its own behavior. These expectations are not just habits. In modern physics, they are expressed as invariances, statements that certain transformations do not change the fundamental form of the laws. That word, invariance, is worth holding gently. It does not say nothing changes. It says that when you change your description in a controlled way, the universe does not punish you by changing its fundamental behavior. Invariance is why you can translate an equation from one place to another, or compare measurements made in different laboratories. It is also why physics can be universal rather than local folklore. Symmetry is the broader family that invariance belongs to. Symmetry in physics means that a transformation leaves something important unchanged. Sometimes it is spatial, like rotating a sphere. Sometimes it is deeper, like changing a reference frame or adjusting a field description in a way that does not alter observable outcomes. Modern fundamental physics leans heavily on symmetry principles, both in quantum theory and in relativity, Because symmetry tells us what kinds of laws are possible and what kinds of interactions can fit together without contradiction. There is a famous bridge between symmetry and conservation. If the underlying rules do not change with time, then there is a conserved quantity we call energy. If the rules do not change as you shift your experiment through space, then there's a conserved quantity related to momentum. If the rules do not change as you rotate your perspective, then there's a conserved quantity related to angular momentum. In the language of modern physics, this connection is made precise by Noether's theorem, which links continuous symmetries of a system's description to conserved quantities. This is not a decorative detail. Conservation laws are among the most stable tools in science. They allow us to treat change as accounting rather than chaos. Energy can shift form, but it does not simply evaporate from a closed description. Momentum can be transferred, but it is not conjured without cause. With conservation in hand, you can understand the motion of a satellite, the heating of a metal, or the spectrum of light from a star using the same underlying bookkeeping. Conservation is one of the reasons physics can build long chains of explanation without collapsing into ad hoc storytelling. Beneath conservation sits another requirement: consistency. Physics is not only about what happens, but also about what is not allowed. A good theory should not contradict itself, and it should not let you build paradoxes by following its own rules. Over centuries, physicists learned that demanding consistency is not merely philosophical neatness. It can be a generator of discovery. When a set of assumptions conflicts with another set of assumptions, the tension forces a deeper picture. Relativity is a clean example of this. Special relativity emerged from insisting that the laws of physics should treat all uniformly moving observers fairly, and that light in vacuum is not an accident of one particular viewpoint. Those demands reorganized our ideas of space and time into a single structure where measurements depend on motion, but the laws remain the same. General relativity carried the principle further by describing gravity as geometry. Matter and energy are associated with the curvature of spacetime, and free motion follows the shape of that geometry. This focus on perspective might sound abstract, yet it has a quiet payoff. It turns physics into the study of relationships and constraints, rather than the study of pushes and pulls alone. Instead of imagining that nature must choose a different rule for every situation, we look for a small number of constraints that apply everywhere, and then let the details follow. Modern physics also changed what we mean by empty. In everyday life, empty space feels like absence. In theory, space can still host structure. Fields can exist even where there are no particles, and fields can carry energy and momentum across space. In quantum field theory, fields are treated as fundamental ingredients, and what we call particles are understood as quantized excitations of those fields. We do not need the full machinery yet. For now, the point is simply that the rules of physics can be deeper than the objects we talk about. Objects are described in terms of rules, not the other way around. In that sense, rules feel prior. They are the framework that allows things to be stable, repeatable, and recognizable. At this point, it is natural to ask whether the laws could have been different. Physics can explore alternative laws inside models, but it cannot step outside reality to compare a shelf of universes. What we can say, with evidence, is that the laws we measure appear remarkably stable across the observable universe. We test this stability by examining light that has traveled for immense spans of time, and by checking whether the same atomic fingerprints appear in distant places. Within measurement limits, nature seems to be playing the same game everywhere we can see. There is also a gentle mystery about simplicity. Fundamental laws are often compact compared to the complexity they produce. A small set of constraints can generate enormous diversity, from the structure of atoms to the architecture of galaxies. This is not guaranteed by logic. It is a discovered feature of our universe. It is one reason science works. Nature is rich, but not arbitrary. It also helps to be careful about what a law is not. A law is not a perfect diary of every detail that ever happens. Many laws in textbooks are idealizations that become exact only under certain conditions, like frictionless motion or perfectly isolated systems. In real life, we use layers of description. A deeper theory explains when a simpler law works and when it must be corrected. This is why physics can be both confident and humble at the same time. The confidence comes from patterns that repeat stubbornly across experiments. The humility comes from knowing that every law we write is part of a model, and models are tools that can be sharpened. Symmetry fits naturally into this picture because it is a way of stating what should not matter to the behavior of nature. When a symmetry holds exactly, it is like a strict grammatical rule. When a symmetry is broken, it can be like choosing one option among many that were allowed in principle, producing new structure without abandoning the deeper framework. That idea, symmetry and symmetry breaking, sits near the center of modern fundamental physics. So the opening of our story is not a bang. It is a quiet claim. The universe is lawful in the sense that it has stable patterns, and the deepest patterns are expressed as symmetries, invariances, and consistency. Once you accept those, everything else can be built step by step. And if your day has been heavy, you do not need to solve why the rules exist. You can rest in the fact that the world holds together. The same consistency that guides distant starlight also guides your breathing right now. Let that steadiness do the work for you, and let the day loosen its grip as you drift towards sleep. Chapter 2. Energy, the first currency of reality. Before particles, before atoms, before even the idea of objects moving through space, physics places energy at the center of its descriptions. Energy is not a thing you can hold, and it is not a substance that flows like a fluid, yet it is one of the most reliable concepts ever discovered. Wherever change happens, energy provides the accounting. It is the common language that allows very different physical processes to be compared, predicted, and understood within a single framework. In everyday life, energy is often associated with effort or fuel, something you run out of at the end of a long day. In physics, energy is more subtle and more universal. It is a measure of the ability of a system to change, to do work, or to rearrange itself. This definition is intentionally broad because energy appears in many forms that look unrelated on the surface. Motion carries energy, but so does position in a gravitational field. Vibrations carry energy, as does light. Even the quiet structure of empty space carries energy in modern physical theories. One reason energy occupies such a foundational role is that it is conserved under a wide range of conditions. When physicists say energy is conserved, they do not mean that nothing ever changes. They mean that when a system is described carefully enough, energy does not simply vanish or appear from nowhere. It transforms. Kinetic motion can become heat. Stored chemical energy can become light. Gravitational energy can become radiation. The bookkeeping holds even when the forms change dramatically. This conservation is not an arbitrary rule added by hand. It is deeply connected to the structure of time itself. When the underlying laws of physics do not change from one moment to the next, energy conservation follows as a consequence. This insight, formalized in modern theoretical physics, explains why energy plays such a universal role. As long as the rules of nature do not depend on when you perform an experiment, energy remains a stable quantity you can track. Because of this, energy can be treated as a kind of currency of reality. Different processes exchange energy in predictable ways, much like economic transactions exchange money without changing the total balance. A star shines by converting energy stored in mass into radiation. A falling object speeds up by converting gravitational energy into motion. A cooling cup of tea releases energy into its surroundings as heat. The details differ, but the accounting remains consistent. Importantly, energy does not require matter to exist. In classical physics, fields such as the electromagnetic field can carry energy through empty space. A beam of light travels through a vacuum, transferring energy from its source to whatever absorbs it later. This already weakens the idea that energy is tied exclusively to material objects. Modern physics goes further. In quantum field theory, the fields themselves are fundamental, and energy is associated with their configurations and excitations, even when no particles are present. This leads to a subtle but important shift in perspective. Instead of thinking that matter possesses energy, it can be more accurate to say that energy configurations give rise to what we perceive as matter. Stable patterns of energy in fields behave like particles. They have mass, they persist over time, and they interact in regular ways. In this view, matter is not the starting point. Energy arrangements are. The relationship between mass and energy reinforces this idea. In relativity, mass is understood as a concentrated form of energy. Objects resist acceleration because of the energy bound up in their existence. This equivalence explains why processes involving very large energies can create particles, and why particles can disappear by releasing energy. Matter and energy are not separate categories. They are different expressions of the same underlying quantity. Energy also plays a central role in determining what processes are allowed to happen. Physical systems tend to evolve towards states that are energetically favorable under their constraints. This tendency does not require intention or foresight. It follows from statistical behavior when many degrees of freedom interact. A ball rolls downhill because lower gravitational energy states are more accessible. Heat flows from hot to cold because energy spreads among available modes. Chemical reactions proceed because certain energy configurations are more stable than others. At larger scales, energy shapes the structure of the universe itself. Stars form when gravitational energy pulls matter together, heating it until nuclear processes become possible. Galaxies form because gravitational energy dominates over other interactions across vast distances. The expansion of the universe is described in terms of energy content, including matter energy, radiation energy, and more mysterious components associated with the structure of space-time. Even the concept of temperature is an expression of energy. Temperature measures how energy is distributed among microscopic degrees of freedom. A hotter system has energy spread among more intense or more numerous motions at small scales. This statistical view connects the microscopic and macroscopic worlds, showing how large-scale behavior emerges from energy distribution rather than detailed control. One of the most counterintuitive aspects of modern physics is that energy can be associated with what appears to be emptiness. In quantum theory, the lowest energy state of a field is not truly zero. Fluctuations remain, constrained by uncertainty relations. These fluctuations do not allow unlimited energy extraction, but they influence measurable phenomena, such as shifts in atomic energy levels and subtle forces between objects placed very close together. Empty space, in this sense, is structured rather than inert. This does not mean energy is free or unbounded. Conservation laws still apply. What it means is that the baseline of reality is not a static void. It is an active stage with properties that matter. This idea prepares the ground for later chapters, where fields and spacetime themselves become central characters in the story. Energy also provides a unifying bridge between different branches of physics. Mechanics, thermodynamics, electromagnetism, quantum theory, and relativity all speak the language of energy, even when their mathematical tools differ. This shared concept allows insights from one domain to inform another. When a new phenomenon is discovered, one of the first questions physicists ask is how energy flows and transforms within it. Despite its centrality, energy is not something you can point to directly. You infer it from behavior. You calculate it from motion, position, field strength, or statistical distributions. In this way, energy is similar to the rules discussed earlier. It is not a tangible object, but a relational quantity, defined through how systems change and interact. There are limits to what energy can explain on its own. Conservation tells you what is possible, but not necessarily what will happen in detail. Two processes may both respect energy conservation while producing very different outcomes. To refine predictions, additional principles are needed, including the structure of interactions and the probabilistic rules of quantum theory. Still, energy sets the broad boundaries within which all physical stories must fit. It is also worth noting that energy conservation, while extraordinarily robust, must be applied carefully. In expanding spacetime, defining a global conserved energy becomes subtle. Energy can be locally conserved while global definitions lose their simplicity. This does not break physics. It reflects the fact that conservation laws depend on symmetries, and expanding space changes the symmetry structure of the universe. The deeper lesson remains intact. Energy is meaningful where the appropriate conditions apply, and those conditions are part of the physical description. From the quiet behavior of atoms to the life cycle of stars, energy quietly governs what can happen and what cannot. It does not choose outcomes, but it constrains them. It does not explain why the rules exist, but it expresses how those rules operate in practice. If the previous chapter established that reality follows rules, energy is how those rules keep score. It is the common measure that allows wildly different processes to be compared without confusion. Without energy, physics would fragment into unrelated descriptions. With it, the universe becomes a connected whole. And there is something gently existential in this idea. Everything you experience, every sensation, every thought, every memory, corresponds to energy moving, transforming, and redistributing itself in highly organized ways. When your day feels scattered, remember that beneath the surface, nothing is truly lost. Energy flows, patterns change, but the accounting holds. In that steadiness, there is room to rest, knowing that you are part of a universe that never wastes, what it has. Chapter 3: Fields before particles. For much of human history, matter was imagined as the fundamental building block of reality. Objects seemed solid, bounded, and persistent, while empty space appeared to be nothing more than a passive backdrop. Physics slowly reversed this intuition. As our understanding deepened, it became clear that what we perceive as particles are not the starting point. Beneath them lies something more continuous and more subtle: fields. A field, in physics, is not a material substance and not a force acting at a distance in the old sense. It is a way of assigning physical properties to every point in space and time. Instead of asking where an object is, a field description asks what the state of space itself is like at each location. Temperature in a room is a familiar example. At every point, the temperature can have a value, even if no thermometer is placed there. The temperature field exists as a description of reality, not as a separate object. The concept of fields entered physics through the study of electricity and magnetism. Early experiments showed that electric and magnetic effects could influence objects without direct contact. Rather than imagining invisible strings pulling at a distance, physicists like Faraday proposed that space itself was altered by the presence of electric charges and currents. These alterations formed patterns that could be mapped and visualized. Later, Maxwell unified these ideas into a coherent theoretical framework, showing that changing electric and magnetic fields propagate through space as waves. Light itself turned out to be one of these waves. This was a profound shift. Light was no longer a stream of tiny objects flying through emptiness. It was an oscillation of a field that exists everywhere. Even where there are no charges, the electromagnetic field has a state. When disturbed, it can carry energy and momentum across vast distances without requiring a material medium. Classical field theory already suggested that fields are more fundamental than the objects that interact through them. However, it was the development of quantum theory that fully overturned the particle-first picture. In quantum mechanics, particles behave in ways that resist classical intuition. They spread out, interfere with themselves, and cannot always be said to have definite positions until measured. These behaviors hint that particles are not little solid beads moving through space, but manifestations of something more extended. Quantum field theory makes this explicit. In this framework, each type of particle is associated with a corresponding field that permeates all of space. An electron is not a tiny object traveling through emptiness in the classical sense. It is a localized excitation of the electron field. Where the field is excited in a particular way, we observe a particle. Where it is not, the field still exists, quietly defining what could happen. This perspective removes the sharp boundary between presence and absence. A region of space without particles is not empty in the fundamental sense. It is a region where fields are in their lowest energy configurations. These configurations still have structure and still obey the rules of the theory. The difference between empty space and matter is not the presence or absence of fields, but how those fields are arranged. One advantage of field-based descriptions is their compatibility with relativity. Relativity teaches that space and time are intertwined and that physical laws should look the same to different observers, regardless of their motion. Fields naturally fit this requirement. They can be defined across space-time in a way that respects these symmetries. Particles, treated as primary objects, struggle to maintain this consistency at high energies and small scales. Fields handle it more gracefully. Fields also provide a natural language for interactions. In older pictures, forces were imagined as mysterious influences acting across distance. In field theory, interactions occur because fields influence one another locally. A charged particle responds to the electromagnetic field at its location. Changes in that field propagate outward at finite speed. There is no need for instantaneous action across space. Everything happens through local interactions of fields with fields. As theories developed, new fields were introduced to account for different interactions. Each fundamental interaction corresponds to a field structure with specific properties. The richness of the physical world arises not from an assortment of independent particles, but from the interplay of a relatively small number of fundamental fields obeying consistent rules. An important feature of fields is that they are inherently relational. A field value at a point is meaningful because of how it relates to neighboring points and to other fields. This relational nature aligns with the broader theme that physics is about patterns and constraints rather than isolated objects. Fields encode these patterns continuously, without requiring discrete pieces of matter as the starting assumption. Fields also clarify why particles of the same type are truly identical. Every electron in the universe has exactly the same properties because every electron is an excitation of the same underlying field. There is no individuality at the fundamental level. What we call particles are indistinguishable because they are not separate entities in the deepest sense. They are different manifestations of a single universal structure. This idea has experimental support across many domains. Particle accelerators do not reveal smaller and smaller hard objects as energy increases. Instead, they reveal new excitation modes, new patterns of behavior consistent with field descriptions. When sufficient energy is concentrated, new particles can appear, not because something was hiding inside space, but because the fields allow new excitations under those conditions. Fields also play a central role in understanding stability. A particle persists because the corresponding field configuration is stable or long-lived under the governing rules. When a configuration is unstable, it decays into other excitations. This decay is not a particle falling apart like a mechanical object. It is a reorganization of field patterns into forms that are more consistent with the underlying dynamics. Even concepts like vacuum and emptiness become richer in a field-based view. The vacuum is not a featureless void. It is the state of all fields at their lowest allowed energies. This state can have observable consequences. Subtle effects arise from fluctuations constrained by quantum principles, influencing measurable quantities without violating conservation laws. These effects confirm that fields are physically real, not just mathematical conveniences. At the same time, it is important to avoid overstating what is known. Quantum field theory is extraordinarily successful within its tested range, but it is not the final word. Combining it fully with gravity remains an open challenge. Nonetheless, within its domain, the field picture has passed every experimental test with remarkable precision. It has predicted phenomena before they were observed and explained patterns that would otherwise seem disconnected. Crucially, fields help unify the story of reality. Instead of juggling separate categories for matter, forces, and radiation, fields offer a common foundation. Particles are not exceptions to the rules, they are expressions of them. Interactions are not mysterious influences. They are local responses within a continuous structure. This does not mean that particles are unreal. They are real in the sense that waves on the surface of the ocean are real. A wave is not separate from the water, yet it has observable properties, carries energy, and can have dramatic effects. Similarly, a particle is not separate from its field, yet it behaves in ways that justify treating it as an entity in many contexts. Understanding this layered description is part of the maturity of physics. At different scales and under different conditions, different pictures are useful. Fields are fundamental, but particles are practical. Both are valid within their domains, and the transition between them is governed by clear principles rather than philosophical preference. By placing fields before particles, physics adopts a quieter, more continuous view of existence. Reality is not built from isolated points, but from extended structures that fill space and evolve smoothly according to consistent rules. What we experience as solid and discrete emerges from something far more fluid and interconnected. There is a quiet comfort in this idea. You are not a collection of separate pieces moving through emptiness. You are part of a continuous fabric, a temporary pattern within fields that stretch across the universe. Nothing about you is truly isolated. Even in stillness, the fields remain, supporting the gentle continuity of existence. When the day feels fragmented, it can help to remember that beneath it all, reality itself is seamless. Chapter 4: The Quantum Layer of Reality. When physics peers deeply into nature, past atoms and past the idea of continuous fields behaving smoothly, it encounters a layer where intuition weakens and precision becomes essential. This is the quantum layer of reality. It is not a different universe hidden behind the familiar one, but a deeper description of the same world, revealed when interactions occur at very small scales or involve very small amounts of energy. Quantum physics does not replace classical physics or field theory. It refines them, explaining why they work where they do and where their limits lie. At the quantum level, nature does not behave like a collection of tiny objects following clear trajectories through space. Instead, physical quantities that appear continuous at larger scales come in discrete packages. Energy, angular momentum, and other properties do not vary smoothly without limit. They appear in specific allowed amounts. This discreteness is not imposed by measurement tools or experimental imperfections. It is a property of reality itself, confirmed repeatedly across experiments involving light, atoms, and subatomic systems. This realization marked a turning point in physics. Classical theories assumed that if you could look closely enough, you would see smaller versions of the same behavior. Quantum theory showed that this assumption fails. At sufficiently small scales, the rules governing change take on a different character. Predictability becomes statistical rather than exact, and outcomes must be described in terms of probabilities rather than certainties. Probability in quantum physics is not a statement about ignorance in the everyday sense. It is not that particles secretly know what they will do while observers lack the information. Instead, the theory itself assigns probabilities as fundamental features. Even when all available information is accounted for, only the likelihood of different outcomes can be predicted. This shift was deeply unsettling when first encountered, but it has proven to be one of the most accurate descriptions of nature ever devised. The wave-like behavior of quantum systems is central to this picture. Particles such as electrons do not travel as localized points along definite paths in the classical sense. They are described by wave-like entities that encode probabilities for where interactions may occur. These waves can spread out, overlap, and interfere, producing patterns that cannot be explained by classical particles alone. Experiments involving interference confirm that this wave-like description is not metaphorical. It reflects real, measurable behavior. At the same time, quantum systems can produce localized, particle-like outcomes when interactions occur. A detector registers a specific event, a screen shows a single spot, a measurement yields a definite value. Quantum theory unites these seemingly contradictory aspects without reducing one to the other. The wave description governs how probabilities evolve, while interactions produce concrete outcomes. Neither picture alone is sufficient. Together, they form a consistent framework. This dual character should not be understood as particles switching between being waves and being objects. Instead, it reflects the limits of classical categories. Quantum entities are neither classical particles nor classical waves. They are described by mathematical structures that encompass aspects of both while remaining fundamentally distinct. Attempts to force them into familiar boxes tend to generate confusion rather than clarity. Another defining feature of the quantum layer is uncertainty. Certain pairs of physical properties cannot be simultaneously specified with arbitrary precision. This is not due to clumsy instruments or experimental disturbance alone. It arises from the structure of the theory itself. Position and momentum, for example, are linked in such a way that sharpening one inevitably blurs the other. This uncertainty places a fundamental limit on how sharply nature can be described at small scales. Uncertainty does not imply disorder or randomness in the everyday sense. Quantum systems evolve according to precise mathematical rules. What uncertainty limits is the set of questions that can be meaningfully asked at the same time. The universe is not hiding answers from us. It is telling us that certain combinations of questions do not correspond to physical reality. Measurement plays a special role in quantum theory, often misunderstood as requiring consciousness or observation in a philosophical sense. In physics, a measurement is simply an interaction between systems that leads to a definite outcome recorded in the macroscopic world. When a quantum system interacts strongly with its environment, the delicate wave-like superpositions that describe multiple possibilities become effectively inaccessible. The system appears to settle into one outcome, not because reality chooses in response to observation, but because interactions distribute information into the environment. This process, known as decoherence, explains why quantum behavior fades at larger scales. The world around us is constantly interacting, exchanging energy and information. These interactions suppress quantum interference effects, allowing classical behavior to emerge. Chairs, planets, and people do not display obvious quantum superpositions because their interactions with the environment are overwhelming. Quantum physics remains valid, but its distinctive features are averaged out. Importantly, decoherence does not add new rules to quantum theory. It follows from applying quantum principles consistently to larger systems. This reinforces the idea that the quantum layer is not separate from the everyday world. It underlies it, shaping its possibilities while remaining mostly hidden from direct experience. Quantum theory also reshapes how we think about causality. In classical physics, causes lead to effects along clear chains through space and time. In the quantum framework, correlations can exist between systems that cannot be explained by local causes acting independently. Entangled systems exhibit linked behavior even when separated by large distances. These correlations do not transmit signals faster than light, preserving relativistic causality, but they challenge simple narratives about independent objects. Rather than signaling a breakdown of logic, entanglement reveals that the fundamental units of reality are not isolated entities, but parts of a shared description. The state of one system can only be fully specified in relation to another. This relational aspect aligns naturally with the field-based picture introduced earlier, where properties are not owned in isolation, but arise from patterns within a larger structure. Despite its strangeness, quantum theory is not speculative philosophy. It is grounded in experimental success unmatched by any other physical theory. Predictions derived from quantum principles have been confirmed to extraordinary precision across countless experiments. Technologies that define modern life, from semiconductors to lasers, rely directly on quantum behavior. The theory works not because it is comforting, but because nature agrees with it. Still, quantum theory does not answer every question. It tells us how probabilities evolve and how outcomes are distributed, but it does not explain why a particular outcome occurs in a specific instance. This limitation is not a flaw, but a feature. Physics describes patterns, not destinies. It provides a framework for understanding regularities without claiming to dictate individual events. Crucially, the quantum layer does not undo the ideas developed earlier. Energy remains conserved within appropriate conditions. Fields remain the underlying structures. What quantum theory adds is a refinement of how these concepts behave when examined closely. Energy comes in discrete amounts. Fields fluctuate even in their lowest states. Interactions follow probabilistic rules rather than deterministic trajectories. The emergence of the classical world from the quantum layer is one of the great achievements of modern physics. It shows how certainty arises from probability, how stability emerges from fluctuations, and how the familiar world is not contradicted by quantum principles but supported by them. Classical behavior is not an illusion. It is an approximation that becomes extremely accurate when many interactions occur together. Understanding the quantum layer encourages intellectual humility. It reminds us that intuition evolved for survival at human scales, not for grasping the deep structure of reality. When intuition fails, careful reasoning and experiment take its place. The reward is not confusion, but a deeper coherence that connects phenomena once thought unrelated. There is also a quiet philosophical shift embedded here. The quantum world suggests that reality is not fully defined until interactions occur, not because minds intervene, but because relationships matter more than isolated attributes. Existence is not a static inventory of properties, but a dynamic web of possibilities constrained by consistent rules. As the day slows and thoughts begin to loosen, this perspective offers a gentle reflection. You do not need to be fully defined at every moment. Like the quantum world beneath you, some things can remain open, unresolved, and still perfectly real. Uncertainty does not mean instability. It means possibility. And within that quiet field of possibilities, it is safe to rest. Chapter 5. How particles emerged from fields. If fields are the continuous fabric of reality, then particles are the recognizable shapes that fabric can take. They are not added afterward as separate ingredients, nor are they tiny solid objects hidden inside fields. In modern physics, particles emerge as stable, repeatable patterns of excitation within underlying fields. This shift in perspective changes not only how particles are defined, but why they exist at all. In classical thinking, a particle is something that simply is. It has a position, a mass, and perhaps a charge, and it moves through space as an individual entity. Field-based physics replaces this picture with something quieter and more structural. A particle exists because a field can support a localized disturbance that behaves consistently over time. Where that disturbance persists, interacts, and can be counted, we give it a name and treat it as a particle. This idea is not philosophical decoration. It is grounded in the mathematical structure and experimental success of quantum field theory. Each fundamental type of particle corresponds to a specific field that fills all of space. The properties we associate with particles, such as mass, charge, and spin, arise from how the corresponding field behaves and how it interacts with other fields. The particle is not an independent object traveling through a background. It is an expression of the field itself. One way to understand this emergence is to think in terms of allowed patterns. Fields obey precise rules that limit how they can change. Under certain conditions, these rules permit localized, quantized excitations that do not immediately disperse. These excitations carry energy and momentum, interact predictably, and can be created or destroyed in interactions. Because they are stable enough to persist, they become the building blocks of matter. Stability is crucial here. Many possible disturbances in a field exist only fleetingly. They appear and vanish too quickly to be treated as particles. Others endure because the field's dynamics support them. A particle is, in this sense, a stable compromise between the tendency of a field to spread out and the constraints that hold certain configurations together. Where this balance is achieved, matter emerges. Mass plays a central role in this stability. In field theory, mass is not an intrinsic label attached arbitrarily to particles. It reflects how a field responds to changes in motion and how much energy is associated with a given excitation. Massive particles correspond to excitations that require energy to sustain and resist acceleration. Massless excitations, such as those associated with certain fields, behave differently, propagating freely at characteristic speeds. The origin of mass itself is tied to field interactions. Some fields interact with a pervasive background field in such a way that their excitations acquire mass. Without this interaction, many particles would behave as if they were massless, radically altering the structure of matter. The existence of stable atoms, molecules, and solids depends on this mechanism. Matter, as we know it, is possible because fields do not exist in isolation but influence one another. Charge, too, emerges from field behavior. A charged particle is not a tiny object carrying a miniature tag. It is an excitation that couples to another field in a specific way. This coupling determines how the particle responds to forces and how it influences other excitations. The regularity of these couplings explains why particles of the same type behave identically across the universe. They are all manifestations of the same underlying relationships. Spin, often misunderstood as literal rotation, is another property that emerges from field structure rather than mechanical motion. It reflects how a field excitation transforms under changes of perspective, such as rotations. Spin has no classical analog, yet it has concrete physical consequences, shaping the structure of atoms and the behavior of matter at all scales. Its existence underscores how particle properties arise from deep symmetries rather than visible mechanisms. Once particles are understood as field excitations, creation and annihilation become natural processes. In high-energy interactions, energy supplied to fields can reorganize into new excitations. Particles appear not because something is pulled from nothing, but because the field supports new patterns under the right conditions. Conversely, when particles disappear, their energy is redistributed into other excitations or radiation. Nothing fundamental is lost, the fields persist. This perspective also explains why particles are indistinguishable. There is no hidden label that makes one electron different from another. All electrons are excitations of the same field, governed by the same rules. Their apparent individuality arises only from their location and relationships at a given moment. This indistinguishability is not a philosophical claim. It is essential for explaining the structure of matter and the behavior of quantum systems. As particles interact, they exchange energy and momentum through the fields they couple to. These interactions do not require direct contact in the classical sense. Instead, they involve the local influence of fields on one another. What appears as a force between particles is, at the deeper level, a pattern of field interaction. The particle picture remains useful, but it is a convenient shorthand for a more continuous process. Over time, collections of particles can form bound states. Atoms are stable arrangements of field excitations held together by consistent interactions. Molecules extend this stability further, and solids emerge when vast numbers of excitations settle into repeating patterns. None of this requires new fundamental ingredients. Complexity arises from the repeated application of the same underlying field rules. It is important to emphasize that particles are not illusions. They are real in the sense that they produce reliable, measurable effects and can be manipulated experimentally. What changes is the understanding of what kind of reality they have. They are not primary substances, but emergent features, much like waves on water or vibrations in a solid. Their reality lies in their persistence and their role in interactions, not in independent existence. This layered description allows physics to remain coherent across scales. At high energies and small distances, the field picture dominates. At lower energies, particle descriptions become effective and intuitive. The transition between these regimes is not abrupt. It is governed by well-understood principles that explain when particles behave as isolated entities and when their underlying field nature becomes apparent. Crucially, this emergence does not conflict with the quantum layer discussed earlier. Quantum behavior governs how field excitations form, evolve, and interact. The probabilistic nature of quantum theory determines the likelihood of particle creation and decay, while conservation laws constrain the overall process. Fields, energy, and quantum rules work together rather than competing for explanatory priority. By understanding particles as emergent, physics avoids the need for infinite subdivision. There is no requirement to imagine ever smaller objects inside particles. Instead, there is a finite set of fields with specific properties, and the richness of the material world arises from how these fields organize themselves under the constraints of symmetry and interaction. This economy of explanation is one of the quiet strengths of modern physics. This view also reshapes how we think about identity and persistence. A particle persists as long as the field configuration that defines it remains stable. When that configuration changes, the particle ceases to exist as that particle, even though the underlying fields continue unchanged. Existence at the fundamental level is not about permanence, but about pattern. In this sense, matter is not frozen into reality. It is continually being recreated moment by moment as fields maintain certain arrangements. The solidity of the world is a dynamic achievement, not a static fact. Stability emerges from constant activity governed by consistent rules. There is something deeply calming in this picture. You are not made of rigid, unchanging pieces. You are made of patterns that hold together because the universe knows how to support them. When those patterns change, nothing fundamental is lost. The fields remain, ready to form new arrangements. Seen this way, existence is not a fragile exception in an indifferent universe, but a natural expression of its deepest structure. Chapter 6: Forces: How Reality Interacts with Itself. Once particles are understood as stable patterns within fields, a deeper and unavoidable question follows. How do these patterns influence one another? Why does matter attract, repel, bind together, decay, or transform? In physics, the answer is expressed through forces, but not as external agents acting upon otherwise passive objects. Forces are the internal language of reality. They describe how fields respond to fields, how structures within the universe communicate with one another, and how change is possible at all. In everyday experience, forces appear simple. You push a door and it opens. You drop an object and it falls. You bring two magnets close and feel resistance or attraction. These impressions suggest that forces are something applied from the outside. Modern physics replaces this intuition with a more unified picture. There is no moment where a force reaches across empty space to grab an object. Instead, every interaction unfolds locally through the continuous presence of fields that permeate space and time. A particle alters the surrounding field simply by existing as a particular excitation. That alteration is not a message sent outward, but a change in the local structure of reality. Other particles respond not to the distant source, but to the field where they themselves are located. What we experience as force is the consequence of this local response. The universe does not act at a distance. It reacts at every point to the conditions present there. This perspective reshapes causality without breaking it. Causes still precede effects, but influence propagates through structured space rather than jumping instantaneously. This requirement preserves consistency with relativity and prevents paradox. Even at its most subtle levels, reality remains disciplined. Gravity provides the clearest demonstration of this modern view. In classical physics, gravity was treated as an attractive force between masses. In contemporary physics, gravity is better understood as a manifestation of space-time geometry. Energy and momentum determine how space-time curves and objects move according to that curvature. Motion under gravity is not caused by a pull, but by following the natural paths defined by space-time itself. This description has been confirmed by precise measurements, from the motion of planets to the timing of atomic clocks and the detection of faint ripples traveling through space-time. This geometric view of gravity also reveals something deeper about forces. Gravity does not single out specific particles based on their internal properties. Everything with energy participates. This universality is not an accident. It reflects the fact that gravity is tied to the structure of space-time, rather than to a particular field excitation. Reality interacts with itself at the most fundamental level through geometry. Electromagnetism, by contrast, is selective. Only particles with specific properties respond to it. Electric charge determines how strongly an excitation couples to the electromagnetic field. A charged particle modifies the field around it, and that modification influences other charged particles. Neutral particles remain unaffected in most circumstances. This selectivity illustrates how forces arise from specific relationships between fields rather than from universal attraction. At the quantum level, interactions are described with even greater precision. Fields do not influence one another continuously in arbitrary ways. They interact through well-defined processes governed by quantum rules. These processes can be represented as the exchange of quantized disturbances within fields. This language is a powerful computational tool, but it should not be mistaken for a literal mechanical picture. What truly happens is that fields adjust to one another according to strict constraints, producing outcomes that appear as forces between particles. Different interactions dominate at different scales because their associated fields behave differently. Some interactions are confined to extremely short distances, shaping the internal structure of atomic nuclei. Others operate over intermediate distances, giving rise to chemistry and the structure of matter. Still others extend across the cosmos, sculpting galaxies and clusters. These differences emerge naturally from the mathematical consistency of the fields, not from arbitrary tuning. Forces are inseparable from the properties of the particles they affect. A particle's mass, charge, and other characteristics determine how it participates in interactions. These properties are not labels attached after the fact. They are expressions of how the underlying field is allowed to behave. Interaction rules are built into the fabric of the theory itself. This embedded structure explains why forces are so reliable. An electron always responds to electromagnetic influence in the same way, whether it is in a laboratory or in a distant galaxy. A gravitational field affects clocks and trajectories consistently everywhere it exists. The universe does not improvise its interactions. It follows patterns that remain stable across enormous ranges of scale and condition. Forces also determine what kinds of structures can form and persist. Without interaction, particles would pass through one another without consequence. No atoms would form, no molecules would bind, no stars would ignite. Interaction allows energy to be stored, transferred, and redistributed. It allows patterns to stabilize long enough to become meaningful structures. In this sense, forces are not just mechanisms of motion, they are mechanisms of existence. At the same time, forces impose limits. Interactions do not permit all imaginable configurations. Some arrangements are unstable and quickly dissolve. Others exist only under narrow conditions. This selective pressure gives the universe its dynamic character. Change is constant, but not chaotic. Stability is possible, but never absolute. Everything that exists does so under ongoing negotiation between competing interactions. Another defining feature of fundamental forces is locality. Interactions occur through direct contact between fields at specific points in spacetime. Even when correlations appear between distant systems, no usable influence travels faster than allowed by spacetime structure. This ensures that cause and effect remain well-ordered. The universe preserves its own consistency without exception. Forces are also deeply connected to symmetry. Many interactions arise because certain symmetries must be preserved not only globally, but at every point in space and time. Enforcing these symmetries requires fields that mediate interaction. In this sense, forces are not optional features of reality. They are required by the demand that the laws of physics remain the same everywhere. Uniformity gives rise to interaction. As conditions vary, the relative strength of interactions changes. Under ordinary circumstances, some forces dominate experience, while others remain hidden. Under extreme conditions, such as those present shortly after the universe formed or in high-energy experiments, interactions that are usually negligible become decisive. This reveals that forces are aspects of a unified framework rather than isolated phenomena. Despite their diversity, known fundamental interactions fit together coherently. They can be described using compatible principles of fields, quantum behavior, and symmetry. This coherence is not guaranteed by logic alone. It is an empirical discovery supported by decades of observation and experiment. The universe behaves as if it is governed by a small set of deeply connected rules, expressed through interaction. Forces do not act with purpose. They do not aim to create complexity or simplicity. They do not strive toward life or consciousness. They simply follow the rules encoded in the structure of fields. The richness of the universe emerges not from intention, but from consistency applied over immense spans of time. Forces also govern response. They determine how systems react to disturbances, how quickly changes propagate, and how equilibrium is restored or broken. Without interaction, nothing could happen. With interaction, reality becomes active, adaptive, and capable of transformation. Every physical process is an expression of fields responding to fields. Seen from this perspective, forces are not something imposed on the universe. They are the universe engaging with itself. Every attraction, every repulsion, every binding and decay is reality responding to its own state. There is no external influence guiding this process, only internal coherence unfolding moment by moment. This understanding carries a quiet existential reflection. You are not a passive object pushed around by distant causes. You are a temporary, stable pattern within an immense network of interactions. The same principles that bind atoms and guide galaxies also shape your body, your thoughts, and your experience of the world. When the day feels heavy or overwhelming, it can help to remember that you are not separate from the forces at work around you. You are part of the universe interacting with itself, and in that interaction, you are continuously supported. Chapter 7: Spacetime, the stage that isn't empty. For a long time, space and time were treated as a silent background. Space was the container in which objects existed, and time was the universal clock against which motion unfolded. Physics once assumed that this stage was passive, fixed, and indifferent to what happened upon it. Modern science overturned this assumption. Space and time are not empty scaffolding. They are active participants in reality, shaped by energy and matter, and in turn, shaping how everything moves and evolves. The idea that space and time are connected is one of the most profound shifts in human understanding. Rather than existing as separate entities, they form a unified structure called spacetime. Events are not defined by where they happen alone or when they happen alone, but by both together. This unification is not philosophical speculation. It arises directly from experimental facts about how light behaves and how motion affects measurement. One of the key insights that led to this view is that the speed of light in empty space is the same for all observers, regardless of how they move relative to one another. This fact forces a re-evaluation of distance and duration. Measurements of length and time are not absolute. They depend on motion. Space and time adjust themselves so that the underlying laws remain consistent. What one observer calls a distance, another may call a combination of distance and time. Space-time absorbs the difference. This does not mean reality is subjective. It means that space and time are relational. They adapt to preserve the structure of physical law. Space-time is the framework that allows different perspectives to coexist without contradiction. It is flexible, but not arbitrary. As physics progressed, this flexibility revealed a deeper truth. Space-time is not only affected by motion, it is affected by energy itself. Mass, radiation, and all forms of energy influence the geometry of space-time. Rather than gravity being a force acting within space-time, gravity emerges as the curvature of space-time itself. Objects move along paths determined by that curvature, following what appear as natural trajectories rather than being pulled by an invisible agent. This geometric description of gravity has been tested extensively. It explains why time passes at different rates in different gravitational environments, why light bends near massive objects, and why orbits deviate slightly from classical predictions. It also predicts phenomena that would otherwise be inexplicable, such as ripples in space-time produced by accelerating massive systems. These ripples carry energy across the universe, confirming that space-time itself can vibrate and change. The realization that space-time is dynamic marks a decisive break from earlier views. Space is no longer an inert void. Time is no longer a universal metronome. Together, they form a responsive structure that records the presence of energy and dictates how motion unfolds. The stage is part of the play. Space-time also sets the ultimate limits of interaction. Because influences propagate through space-time, there is a maximum speed at which information and energy can travel. This limit is not imposed by technology or material resistance. It is built into the structure of space-time itself. Causality, the order of cause and effect, is protected by this structure. Events outside one another's space-time influence cannot affect each other, preserving consistency across the universe. At very large scales, space-time reveals even more complexity. Observations show that the universe is expanding. Distances between distant galaxies increase over time, not because galaxies are moving through space away from one another, but because space-time itself is stretching. This expansion is not uniform in its effects. Bound systems remain intact, while vast regions grow farther apart. The geometry of space-time evolves. This expansion also influences how energy behaves. Light traveling through expanding space-time changes in character as the space it traverses stretches. This effect is measurable and has been confirmed through astronomical observation. It demonstrates that space-time is not just a passive arena in which energy moves, but an active medium that shapes how energy is distributed. At the smallest scales, space-time presents challenges that remain unresolved. Quantum theory describes fields and particles with extraordinary accuracy, yet it treats space-time as a fixed background. General relativity, which describes space-time dynamics, does not incorporate quantum principles directly. Reconciling these two frameworks is one of the central goals of modern theoretical physics. While many approaches exist, a complete and experimentally confirmed theory of quantum space-time remains beyond reach. Despite this, there are strong indications that spacetime itself may have a deeper structure. Quantum fluctuations, uncertainty, and limits on measurement suggest that spacetime may not be infinitely smooth. Whether it is fundamentally discrete, emergent from more basic entities, or something entirely different is still an open question. What is clear is that spacetime is not merely a mathematical convenience. It has physical consequences that can be measured and tested. Spacetime also plays a crucial role in defining energy and momentum. Conservation laws depend on spacetime symmetries. When spacetime has certain uniform properties, corresponding quantities remain conserved. When those symmetries change, conservation laws take more subtle forms. This deep connection shows that spacetime is intertwined with the very notion of physical quantity. Importantly, spacetime does not exist independently of what inhabits it. Matter and energy tell spacetime how to curve, and spacetime tells matter and energy how to move. This mutual relationship removes the idea of a universe assembled from separate components. Instead, reality is a network of relationships, with spacetime as one of its central expressions. At human scales, spacetime feels stable and absolute. Floors do not curve perceptibly. Time seems to pass at the same rate from moment to moment. These impressions are accurate approximations under ordinary conditions, but they are approximations nonetheless. The deeper reality is more fluid, adjusting subtly but relentlessly to motion and energy. Understanding spacetime also reframes the notion of emptiness. Even where there is no matter, spacetime remains. It can stretch, curve, and carry disturbances. It defines what is possible and what is forbidden. Empty space is not nothing. It is a structured arena with properties that influence every physical process. This view aligns naturally with the field-based picture developed earlier. Fields exist within spacetime, but they also interact with its geometry. Energy carried by fields contributes to curvature, and curvature influences how fields evolve. The universe is not divided into matter, forces, and space as separate layers. It is a unified system in which each aspect participates in shaping the whole. Spacetime also shapes the concept of time itself. Time is not a universal flow shared identically by all observers. It is a dimension woven together with space, experienced differently depending on motion and gravitational environment. Yet this variability does not undermine order. Instead, it preserves consistency across perspectives. Each observer experiences a coherent sequence of events, even though different observers may disagree on durations and distances. The flexibility of spacetime allows the universe to remain self-consistent. Without this adaptability, the laws of physics would fracture under differing conditions. Spacetime absorbs differences in perspective, ensuring that physical laws remain intact. At the largest scales, spacetime tells a story of evolution. The universe has a history not just of changing matter, but of changing geometry. Early conditions differed profoundly from those of the present, and future conditions will differ again. Spacetime is not static. It participates in the unfolding of cosmic history. Yet within this vast dynamism, there is remarkable stability. Local spacetime behaves predictably. Physical processes repeat with high precision. The same principles apply in laboratories and in distant galaxies. This balance between change and regularity is one of the most striking features of the universe. Seen in this light, spacetime is not merely where things happen. It is part of what happens. It records energy, shapes motion, and limits interaction. It is both stage and actor, both container and participant. There is a quiet existential resonance in this understanding. You are not moving through an empty backdrop. You are embedded in a living structure that responds to every form of energy, including your own. Every moment of your life is a path traced through space-time, supported by the same geometry that guides stars and galaxies. When the day feels overwhelming, it can be calming to remember that you are held within a universe whose very fabric is stable, responsive, and vast. Time carries you forward gently, and space makes room for you to exist. Chapter 8. From Particles to Atoms to Structure. Once particles exist as stable excitations of fields and can interact through fundamental forces within space-time, a new question emerges naturally. How does complexity arise? How does reality move from isolated particle interactions to atoms, from atoms to matter, and from matter to the vast structures that fill the universe? The answer lies not in new fundamental laws, but in the quiet accumulation of stable arrangements. Structure is not imposed on reality from above. It grows organically from the rules already in place. At the most basic level, particles rarely exist alone for long. Interactions guide them into relationships that reduce overall energy while respecting quantum and relativistic constraints. These relationships are not choices. They are outcomes determined by how forces and fields behave. When conditions allow certain configurations to persist longer than others, those configurations become the building blocks of structure. Atoms represent one of the earliest and most important examples of this process. An atom is not a miniature solar system with particles orbiting in neat paths. It is a quantum structure defined by probability distributions and interaction rules. Negatively charged particles do not circle a central core like planets. Instead, they occupy regions where their presence is allowed by quantum constraints and energy balance. These regions are stable not because particles are fixed in place, but because the overall configuration resists change. The stability of atoms depends on a delicate balance. Attractive interactions draw components together, while quantum principles prevent collapse into a single point. This balance is not accidental. It arises naturally from the mathematical structure of quantum mechanics combined with electromagnetic interaction. If either aspect were absent or altered significantly, atoms would not exist in their familiar form. Once atoms form, new possibilities open. Atoms can interact with one another through their outermost structures, forming bonds. These bonds are not rigid connections, but shared arrangements of probability and energy. When atoms bond, they do not lose their identity entirely. They enter into collective states that are more stable than the atoms would be alone under the same conditions. From these bonds, molecules emerge. Molecules are not merely collections of atoms placed side by side. They are unified quantum systems with properties that cannot be reduced to their individual parts. Shape, reactivity, and stability all arise from how electrons are distributed across the entire molecule. Chemistry, at its core, is the study of how these distributions change and how new stable arrangements form. As molecules accumulate, matter begins to exhibit collective behavior. Solids, liquids, and gases are not distinguished by what they are made of, but by how their components are arranged and how freely they can move. In solids, atoms or molecules settle into repeating patterns, held in place by balanced interactions. In liquids, these patterns loosen, allowing flow while maintaining cohesion. In gases, interactions are weaker and components move freely through space. None of these states require new fundamental forces. They emerge from the same interactions acting under different conditions. Temperature, pressure, and density influence how energy is distributed among particles, and that distribution determines which structures are favored. Order and disorder are not opposites imposed by design. They are outcomes of how energy spreads and how interactions constrain that spread. As structures grow larger, statistical behavior becomes increasingly important. Individual quantum events blur into predictable averages. While the behavior of a single particle may be uncertain, the behavior of many particles together becomes remarkably reliable. This transition from microscopic uncertainty to macroscopic stability is one of the quiet miracles of physics. It explains why tables feel solid, why water flows, and why materials respond consistently to stress and heat. At still larger scales, gravity begins to dominate structure formation. While electromagnetic interactions govern atoms and molecules, gravity governs how large collections of matter behave over long distances. Dust clouds collapse under their own gravity, heating as they compress. When conditions allow, these clouds give rise to stars. Within stars, energy flows and balances determine long-term stability. Structure becomes self-sustaining. Stars are not static objects. They are dynamic systems maintained by equilibrium between opposing tendencies. Gravity pulls inward, while energy generated in the core pushes outward. This balance can persist for immense spans of time, allowing stars to shine steadily. When the balance shifts, stars change, evolve, or end their lives in dramatic transformations that redistribute matter back into space. From stars come heavier elements, forged under extreme conditions. These elements are dispersed through space and incorporated into new generations of stars, planets, and smaller structures. In this way, structure builds upon itself. Each generation provides new materials and new possibilities. Complexity increases not because the laws change, but because the outcomes of those laws accumulate. Planets form as matter settles into stable orbits around stars. On some planets, conditions allow complex chemistry to persist over long periods. Surfaces solidify, atmospheres form, and cycles of energy flow emerge. These cycles can drive further organization, creating layered structures that interact across scales. Throughout this entire progression, from particles to planets, no step requires special intervention. The same rules operate at every stage. What changes is scale, density, and context. Interactions that were negligible at one level become dominant at another. Constraints that were irrelevant at small scales shape outcomes at large ones. Structure is therefore not a separate feature added to reality. It is the natural expression of interaction over time. Given stable laws, energy, and enough duration, structure is not just possible, it is likely. This perspective also clarifies why structure can be both fragile and resilient. Individual arrangements can be disrupted, yet the overall tendency toward organization persists. Destroy a molecule and others form. Disrupt a star, and new stars arise from its remnants. Structure is temporary, but the capacity for structure is permanent. Importantly, complexity does not violate fundamental simplicity. The underlying laws remain compact and consistent, even as the structures they produce become intricate. This separation between simple rules and complex outcomes is a hallmark of physical reality. It allows predictability without monotony, variety without chaos. Structure also introduces history. Once matter organizes, it carries memory of past interactions. A crystal reflects the conditions under which it formed. A planet bears traces of its formation and evolution. At larger scales, the universe itself carries imprints of its early structure in the distribution of galaxies. Structure is not only spatial, it is temporal. At human scales, this accumulation of structure enables life and consciousness. While physics does not explain experience directly, it explains the scaffolding that makes experience possible. Stable matter, persistent energy flows, and reliable interactions create environments where complexity can sustain itself long enough to observe, reflect, and wonder. Yet even here, nothing fundamental changes. The atoms in your body obey the same rules as atoms in distant stars. The forces that bind your cells are the same forces that bind matter across the universe. Structure does not separate you from the cosmos, it connects you to it. Seen this way, the universe is not a collection of isolated objects. It is a hierarchy of patterns, each emerging from the one before it. Particles form atoms, atoms form matter. Matter forms worlds. Worlds participate in cosmic structure. At every level, the same interactions apply. There is a quiet reassurance in this continuity. You are not an accident layered on top of an indifferent universe. You are a natural outcome of its structure-building tendencies. The same rules that allow atoms to exist also allow you to exist, here and now. As the day winds down, this thought can be grounding. You are made of structures that took immense time to form, guided by rules older than any star you can see. Nothing about you is arbitrary. You are part of a universe that knows how to build, how to hold together, and how to persist gently through change. Chapter 9. Large-Scale Order: Stars, Galaxies, and Patterns. Once matter has assembled into atoms, molecules, and solid bodies, the universe does not stop organizing itself. On the largest scales, a different kind of order emerges, governed primarily by gravity and shaped by the geometry of spacetime. This large-scale order is not imposed by design or direction. It arises naturally from the same physical rules already at work, acting over immense distances and vast durations. Gravity is unique among interactions in that it never cancels out. Electric charges can balance, magnetic fields can neutralize, and many forces operate only over limited ranges. Gravity, by contrast, always adds. Every piece of matter contributes, however slightly, to the gravitational structure of the universe. This cumulative nature makes gravity the dominant architect of large-scale order. In the early universe, matter was distributed with remarkable uniformity, but not perfectly so. Tiny variations in density existed from the very beginning. These variations were not flaws. They were essential. Gravity amplified them. Regions that were slightly denser exerted a slightly stronger gravitational pull, drawing in surrounding matter. Over time, these regions grew denser still, while less dense regions became emptier. From these subtle beginnings, the large-scale structure of the universe emerged. As matter collected under gravity, clouds of gas and dust formed. Within these clouds, gravitational contraction increased pressure and temperature. When conditions allowed, stable energy-generating processes began, and stars were born. A star is not simply a glowing object in space. It is a self-regulating system maintained by balance. Gravity pulls inward, while energy produced in the core pushes outward. This equilibrium can persist for immense spans of time, allowing stars to shine steadily. Stars are factories of structure. Within their interiors, simpler atomic nuclei combine into more complex ones under extreme conditions. These processes release energy that supports the star against gravitational collapse. Over the course of a star's life, matter is transformed. When stars exhaust the configurations that sustain them, they change dramatically, redistributing enriched material back into space. This material becomes the raw substance for future generations of stars and planets. Stars rarely exist in isolation. They form in groups, bound by gravity into galaxies. A galaxy is not merely a collection of stars drifting together. It is a coherent gravitational system, often containing vast amounts of gas, dust, and unseen mass that influences its structure. Galaxies exhibit recognizable shapes, including spirals, ellipticals, and irregular forms. These shapes are not accidental. They reflect the history of interactions, rotations, and mergers that shaped each system. Spiral galaxies display ordered motion on grand scales. Stars orbit a common center, following paths determined by gravitational potential rather than direct attraction to a single massive object. The spiral patterns themselves are not rigid structures. They are density waves, regions where matter temporarily crowds together before moving on. This dynamic order allows galaxies to maintain recognizable forms while remaining constantly in motion. Elliptical galaxies represent a different kind of order. They often result from mergers between galaxies, where previous structures are disrupted and rearranged. The resulting system settles into a new equilibrium, smoother in appearance, but still governed by the same gravitational principles. Even apparent simplicity carries a history of complexity. On scales larger still, galaxies gather into clusters and superclusters. These groupings trace out vast filaments separated by immense voids. The resulting pattern, sometimes called the cosmic web, reflects the underlying distribution of matter shaped by gravity acting over cosmic time. This structure is not random. It carries the imprint of the universe's earliest conditions, preserved across billions of years. The existence of such large-scale patterns reveals an important principle. Order does not require careful tuning at every stage. Once initial conditions and laws are set, gravity naturally amplifies structure. Small differences grow into large features. Uniformity gives way to pattern, and pattern gives rise to hierarchy. Energy flows play a crucial role in shaping these structures. Radiation emitted by stars influences surrounding matter, heating it, dispersing it, or triggering further collapse. Explosive stellar events inject energy into interstellar space, preventing some regions from forming stars too quickly while enabling others to evolve. Large-scale order is therefore not static. It is regulated by feedback between matter, energy, and gravity. Spacetime itself participates in this organization. The expansion of the universe stretches large-scale structures, influencing how matter clusters over time. Expansion does not tear apart bound systems, but it shapes the growth of structure across vast distances. The competition between gravitational attraction and cosmic expansion determines the size and distribution of galaxies and clusters. Importantly, large-scale order does not contradict earlier layers of structure. The same atoms that make up distant stars are governed by the same quantum and electromagnetic principles that govern matter on Earth. The same conservation laws apply. What changes is the dominance of different interactions. At cosmic scales, gravity becomes decisive, while other forces recede into the background. This layered dominance allows the universe to remain coherent across scales. Physics does not need separate rules for stars and atoms. It needs only consistent laws applied under different conditions. The universe builds complexity by shifting which interactions matter most at each scale. Large-scale order also introduces long-term stability. Galaxies can persist for durations vastly longer than the lifetimes of individual stars. The overall pattern of the universe changes slowly, even as local structures evolve. This stability provides a backdrop against which change can occur without erasing all structure at once. Yet this order is not eternal. Galaxies merge, stars exhaust their energy, and structures transform. The universe is dynamic, even at its largest scales. Order is maintained not by permanence, but by ongoing processes that balance creation and dissolution. Observations of large-scale structure provide powerful confirmation of physical theory. The distribution of galaxies, the motion of stars within them, and the behavior of light traveling across cosmic distances all align with predictions derived from gravity and spacetime geometry. These observations reinforce the idea that the same laws operate everywhere, without exception. Large-scale patterns also reveal the limits of our understanding. Some aspects of cosmic structure suggest influences not yet fully explained. Invisible components inferred from gravitational effects shape galaxies and clusters in ways that visible matter alone cannot account for. While their nature remains uncertain, their effects fit consistently within the gravitational framework. This reminds us that physics remains an evolving endeavor, guided by evidence rather than final answers. Despite these open questions, the existence of large-scale order itself is beyond dispute. The universe is not a chaotic scattering of matter. It is structured, layered, and patterned. From the smallest atoms to the largest clusters, relationships persist. This continuity across scales carries philosophical weight. The same gravity that binds galaxies also keeps you grounded. The same atomic processes that power stars operate in the cells of your body. You are not separate from cosmic order. You are embedded within it. There is also a quiet humility in recognizing scale. Stars live for spans of time that dwarf human history. Galaxies evolve over durations that challenge imagination. Yet within this vastness, small-scale structures like life can arise and persist. Large-scale order does not erase smaller meanings. It provides the conditions under which they can exist. As the universe organizes itself, it does not favor significance, it favors consistency. Meaning is not written into cosmic structure, but cosmic structure allows meaning to be experienced. The patterns that shape galaxies also make possible the stability required for reflection and awareness. As the day fades and thoughts slow, this perspective can be gently grounding. You are part of a universe that builds order patiently, without hurry and without waste. Stars form, galaxies evolve, patterns persist, and within those patterns, moments of awareness arise. You do not need to keep up with the cosmos. You already belong to it, held quietly within its vast and steady order. Chapter 10. The Universe Built from Simple Rules. After tracing reality from its deepest foundations to its largest structures, a quiet conclusion comes into focus. The universe does not appear to be built from countless unrelated instructions layered one on top of another. Instead, it is governed by a small set of stable rules that operate everywhere, at all times without exception. From these rules, complexity arises naturally, not through intention or design, but through repetition, interaction, and time. At first glance, this idea can feel counterintuitive. The universe looks complicated. Matter forms intricate structures, systems behave unpredictably, and outcomes seem sensitive to circumstances. Yet when physics strips away surface detail and asks what remains invariant, it repeatedly finds the same underlying principles. energy changes form rather than simply disappearing. Physical influence spreads through local interactions rather than instant jumps across empty space. Regularities do not stop at our horizon. They appear wherever we can test them. What makes this remarkable is not merely that rules exist, but that so few of them are needed. The frameworks used to describe fundamental physics are concise compared to the richness of the phenomena they generate. A compact set of principles gives rise to atoms, chemistry, stars, galaxies, and environments capable of sustaining life. The universe does not require a separate rulebook for each level of complexity. It reuses the same foundational logic endlessly, and that reuse becomes a kind of creative engine. This reuse is what allows reality to scale. The same constraints that govern tiny quantum excitations also govern enormous structures once differences of scale, density, and environment are accounted for. Conservation principles apply in a tabletop experiment and across intergalactic space, even when their interpretation becomes more subtle in curved or expanding spacetime. There is no hidden threshold where physics stops working and something else takes over. Reality remains continuous in its logic even when its appearance changes drastically. One reason simple rules can generate extraordinary complexity is feedback. When the outcome of a process alters the conditions under which that process continues, structure can grow quickly. Gravity pulls matter together, increasing density, which strengthens gravitational attraction further. In stars, energy produced in the interior affects pressure and temperature, which regulates the rate of energy production and helps maintain long-lived balance. In chemistry, the arrangement of atoms influences which reactions are likely next, allowing stable molecules and repeating structures to form. Another key factor is sensitivity. Many systems respond strongly to small differences in initial conditions. Tiny variations can grow over time into dramatically different outcomes. This does not mean the universe is lawless. It means the rules are responsive, and repeated application can amplify differences, especially in systems with many interacting parts. A lawful universe can still be surprising, not because it breaks its rules, but because the rules allow divergence and complex behavior. Crucially, complexity does not undermine predictability at the fundamental level. Physics does not aim to predict every detail of every event. It predicts patterns, constraints, and probabilities. This limited predictability is not a weakness. It is what allows systems to explore many outcomes while remaining governed by the same laws. Order does not require absolute determinism. It requires consistency in how possibilities are generated and in how outcomes are constrained. The simplicity of physical law is also what makes scientific knowledge possible at all. If the universe behaved differently in different places, understanding would remain local and fragile. Because the same rules apply everywhere, insight gained in one context can be extended to others. Observations made on Earth inform our understanding of distant stars. Measurements taken today reveal conditions from the early universe. Science works because nature repeats itself with faithful regularity. This consistency should not be confused with rigidity. Physical laws allow change, transformation, and novelty. They define what is permitted, not what must happen in every detail. Within these boundaries, reality explores possibilities freely. The rules set the grammar, but they do not dictate the story. They make room for both stability and surprise, for predictable averages and unpredictable particulars. A helpful way to see this is through effective descriptions. The universe can be described at many scales, and each scale has its own useful language. At very small scales, we speak of quantum behavior and fields. At intermediate scales, we speak of atoms, molecules, and chemistry. At larger scales, we speak of fluids, thermodynamics, and gravity. These are not competing truths. They are approximations that become accurate in their own domains, because stable rules give rise to stable patterns that can be summarized without tracking every microscopic detail. Statistical physics explains why this works. Even though microscopic motion is too complex to follow particle by particle, large collections follow strong tendencies because there are overwhelmingly many microscopic arrangements corresponding to the same macroscopic condition. This is why thermodynamics feels inevitable. Heat flows from hotter regions to cooler ones because there are vastly more microscopic arrangements that look like energy spread out than arrangements that look like energy concentrated. The arrow of time in everyday experience is not a separate rule added on top. It is an emergent direction that arises from simple constraints acting on huge numbers of degrees of freedom. Phase changes offer another example of emergence. A substance can behave like a solid, a liquid, or a gas, not because the underlying physics changes, but because the same interactions produce different collective patterns under different conditions. Near a transition, small changes in temperature or pressure can reorganize the entire structure. The rules remain the same, yet the world looks new. Nature gains variety without gaining new fundamental laws. The same is true in materials. Electrical conduction, elasticity, and transparency are not new interactions. They are collective behaviors arising from familiar forces and quantum constraints acting on large numbers of particles. A conductor is a material where electrons can move through a lattice with relatively low resistance, while an insulator is one where that motion is strongly restricted. The difference is not a new force, it is a different organization of the same rules. The macroscopic property emerges from microscopic structure, and microscopic structure is shaped by the same few interactions repeating in different arrangements. Another way simplicity reveals itself is through universality. Very different physical systems can share the same large-scale behavior because many microscopic details wash out when enormous numbers of components interact. Near some transitions, materials with different internal structures can display the same characteristic patterns. In fluids, gases, and plasmas, collective motion often follows similar governing principles even when the underlying particles differ. This is not because nature is unimaginative, but because large collections forget many details and remember only the constraints that matter at scale. Modern field theory adds a related insight about scale. When we look at nature at a given scale, we do not need to track every smaller scale detail to make accurate predictions. The influence of very short distance physics can often be summarized into a limited set of measurable parameters that control behavior at the scale we can probe. Many fine-grained features matter mainly through their net contribution, and that net contribution can be captured without listing every microscopic step. In this sense, the universe is describable efficiently because complexity at one scale can often be compressed into simple influences at the next. Simplicity also lives at the level of symmetry. Instead of listing many separate behaviors, physics often states a symmetry principle and lets the consequences follow. Symmetries are not decorative. They help determine what interactions are possible, what quantities remain conserved, and what patterns can persist. The universe looks orderly partly because its rules have deep symmetries built into them, and those symmetries prevent physical behavior from fragmenting into unrelated local exceptions. There is an important humility here. Physics deals in models, and models are not the universe itself. A model is a structured approximation that captures what can be predicted. Over time, models improve and sometimes are replaced by deeper ones. Classical mechanics remains useful, even though relativity refines it. Classical electromagnetism remains useful, even though quantum theory deepens it. Refinement does not imply that physics lacks truth. It implies that truth is approached through layers of accuracy, with older frameworks remaining excellent within their domain of validity. This brings us to the question people often ask quietly: why these rules and not another set? Physics can test, compare, and constrain. It can show which rule sets match observations and which fail. It can explore alternative mathematical possibilities, but it cannot step outside reality to compare our universe with an external catalog. What we can say is that the rules we observe are internally consistent, stable across the observable universe, and astonishingly productive. Within this framework, chance and necessity coexist. The laws constrain what can happen, but they do not fix every detail of what will happen. The specific histories of planets, the timing of particular events, and the local arrangement of matter depend on contingent circumstances. Yet broad patterns recur because the rules recur. The universe is not a scripted play, but it is not random noise either. It is a lawful exploration of possibility. This view reshapes how we think about permanence and change. Structures exist because rules allow them to exist under certain conditions. When conditions change, structures transform. Nothing fundamental is lost. The rules remain. Reality is resilient rather than fragile. A star may end, but the matter it forged continues, and the same laws that guided its life guide what comes next. As the day draws to a close, this understanding can offer calm. You do not need to justify your existence against the vastness of the cosmos. The same simple rules that built atoms, stars, and galaxies also built you. You are not separate from the universe's logic. You are one of its natural outcomes, briefly aware within a lawful world. And if everything is made from simple rules, then rest is not a pause outside reality. Rest is one of the quiet patterns reality makes possible, and you are allowed to let that be enough for tonight. Thank you for staying with me until the end, my friend. If you're still awake and would like to drift a little longer, there's another calm science journey waiting for you on the channel. And if sleep is already close, let the universe keep watch for you tonight. May your thoughts slow, your breathing soften, and your dreams wander safely among the stars. Good night.